Okay, so lesson 5.7, we are talking about solving logarithmic equations. So whenever in math we talk about solving, what we are doing is we are going to be solving for the unknown x, okay, or just whatever the unknown is. I am giving you some number here or something on the left-hand side, and I am saying rearrange the problem and find this unknown. That's what it means to solve an equation. Okay. Logarithmic equations have a extra step when it comes to solving it, and that goes to back to the graph. Right. So if I was to graph a log function, I would have my function looking something like this. And I start to head straight down the bottom. That's because I have a vertical asymptote right here at x of 0. And we've seen that we write the domain for that as x belonging to real numbers, and we've said that our x needs to be bigger than 0. But let's go into this concept a little more, okay? Why do we have that restriction here? Well, when you say x needs to be bigger than 0, what that means is that I cannot take any negative number. So I cannot take the log of some negative number, right? -1 being an example, right? So when x has to be bigger than 0, it means that I have no negative x coordinates. None of these numbers that exist on this side of the graph are valid to plug into this x here. But why? Why? Like the whole part is, why do we have that restriction? Why do we say that it needs to be bigger than 0? So why is it that I cannot take the log of -1 or the log of any negative number, like -2? Well, think about it in terms of exponentials. So you have, y equaling. Well, if you were to solve either one of these examples I've given you here, you would put it into exponential form. So these have a base of 10, right? 10, 10. So if I was to put it in exponential, I'd write it as 10 to the y is equal to -1, right? And same thing over here. Another example, 10 to the -2, or sorry, y is -2. Well, is there a number that you can plug in for this y right here that would solve to negative? Right? Like, think about all the different types of numbers you have. Like, try putting in a decimal, like 0.1, or try putting in a fraction, like 1/3, or try putting in, I don't know, a really large number, like, 200, right? Like, how many versions of numbers and you want to try? But what you will find is that all of these will always give you a positive output. Right? And that goes back to the exponential graph, where an exponential function, right, if I graph 10 to the y, it is always here. It is always in the positive y space. There is no value that will give you a negative number. And the same would be true here, right? Like, there's just another example. Like, there is no number that you can put 10 to the power of that would give you -2. It is not possible. So a constraint for a logarithm is that the inside of the log, okay, so what you call the argument, the inside needs to always be positive. It's to always be positive, okay? And we've seen stuff like this before, when you do like square roots, right? Like, here you would have said, hey, under a square root, this also needs to always be positive, because the root function, you cannot take the square root of a negative number. So the function of a root says you always need to be positive. It's the same with logarithms, okay? So the function of a logarithm says that the input always needs to be positive. So if we do that, what we need to do is we need to set up restrictions when we start our problem, okay? So the question says, solve for x, all right? So as I said in the beginning, you're solving for the unknown, the unknown in the problem. But in order to validate our solutions at the end, we need to say, hey, well, what are the restrictions of x? So your first step before you even approach the problem is state restrictions, okay? You have to state restrictions in the unsimplified version, just the expression or the equation that is given to you. So if my restriction is that the inside of the logarithm always needs to be positive, the way you can write that is you say x plus 4, that's what's on the inside of the logarithm, always needs to be positive, so meaning that it always needs to be bigger than 0, okay? It could be a decimal, but as long as it's bigger than 0. So this is just an inequality, so we're just rearranging it. So we will bring this positive 4 to the other side, and what that means is that as long as x is bigger than -4, you're not going to have a problem taking the logarithm, okay? As long as you're taking values of bigger than -4 and you're substituting it in here, you're going to be okay. Like, you'll be able to get a solution. So there's step 1, just state restrictions, okay? So that's the restriction. And that's like a full mark on an assessment. Just do they understand that logarithms have this restriction, that we have this asymptote that exists. So now when I go to actually solve the logarithm, I want to isolate for x, all right? That's the goal. Like, you're trying to tell me what x equals. So just as you did in like quadratics, linear functions, any other unit, we got to get everything to one side and x on its own on the other, okay? So we got to like essentially undo this logarithm. So this logarithm has a base of 10. To undo it, I'm going to take 10 and put it to the power of 1. So 10 to the power of 1 is now equal to what's on the inside of my logarithm. I'm just undoing the log and writing it as an exponential. So now I have, well, 10 to the 1 is just 10, equaling x plus 4. And then I bring the 4 to the other side of the problem. And then I get 6 is equal to x. And then I check, does that satisfy my constraint, my restriction? Yes, well, 6 is a number that is bigger than -4. So that is a valid solution, okay? And just to get a visual, all right, if you were to graph this, we did graphing log in the other lesson. If I was to graph y is log x plus 4, well, I'd be graphing a function, a log function, that has a horizontal shift of -4. So I'd go in here. That's where my vertical asymptote would be. And my graph would look like this. And what you found is you said, okay, well, what x coordinate gives me an output of 1? When is the x here? What coordinate of x gives me this 1? Well, what we algebraically found was at an x coordinate of 6. You are at a y coordinate of 1, okay? And you can see that we are going to have valid solutions as long as x is bigger than this asymptote here. So another way to approach these problems is if you think of it like a graph, okay? Just go back to the graph and be like, where are we on our domain? So B, let's try it again. Log base 4x plus log 8 equals 2. So in this problem, first step, state restrictions, okay? It doesn't matter what problem, just state restrictions. So restrictions. All right, well, my variable is x, all right? So I only have this term right here that I need to state a restriction for. So I look on the inside of that logarithm, which is just simply x. And then that that inside of that logarithm just needs to be bigger than 0. So in this case, we don't really have any rearranging. That's our constraint. Just x needs to be bigger than 0. Okay, so now let's solve it. Let's get x on its own. Well, what would be the process here? You need to have x on one side of the problem, and you need everything else to the other. So how can we do that? Right? You might be thinking, okay, well, like this one has the x, so I'm going to bring this over here because that's what you're supposed to do. But if we did that, right, so this isn't the right thing to do, but if you did that, you would get 2 log 4, 8. And then you just get this really complicated exponent because you go 4 to the power of that equaling x. Like this is not easy to solve, okay? So bringing that logarithm over on the first step was not the approach to this problem. Hopefully, as you did the homework for the previous lesson when we learned about our laws in logarithms, you can see that this right here, this is your product law. Because we have the same base being 4, and it's separated by an addition. So I can rewrite those two terms there as a single log, and if I did that, that would just be log base 4, and then you multiply the inside terms. So those would be, sorry, not in terms, but inside numbers. So that would be 8x equals 2. Now we can write it as an exponent, okay? Because now we'll have just a much simpler, you have one term now on one side. So if I write it as an exponent, right, that is 8x. I'm going to keep the x on the left here, and I'm going to put the 4 squared on the other side. So I went 4 to the power of 2. Okay, so now I have 8x equaling 16, and then x would be 2. Does that satisfy my constraint that x is bigger than 0? Yes. 2 is a number that is bigger than 0. So the last step is you always got to check your solution, okay? Make sure you check your restrictions. C. So step 1, state your restrictions. And just like in previous videos, at any point, pause the video, try it for yourself, okay? And then I'm going to work through it. So just pause, try it, and then watch the solution. So I need to state restrictions. So I look, well, my variable being x, right? This whole problem is solving for x. What would be my unknown? Not what is my unknown? What would be my restriction based off where my unknown is? So I'm looking at this term right here. So you want to always approach restrictions before you start to simplify it, okay? So my step that I would do next, all right, I'm going to jump ahead here for a second, is I would bring this to up top. So I would write it as log x squared equaling log 8 plus log 2. And the reason you state restrictions before you do any simplification, so this was simplification, is because if you were to state the restrictions for this one right here, you would actually have a completely different restriction than the original problem. This restriction would be, when is x squared bigger than 0? All right, and the proof to this is a little more complicated, but essentially, when is x squared bigger than 0? Well, because there is a square here, that means any number being positive or negative would work. So as long as, so your restriction is the magnitude of x is bigger than 0. And that's because you did it at this step here. So you always want to state restrictions before you simplify, because the true restriction is me saying this term right here, when is log x bigger than 0, all right, or sorry, when is the x bigger than 0, just the inside of the argument, well, that is your restriction. Like, because there is like negative numbers, if you plug a negative number in here, it won't work, all right? So the point I was trying to make in this beginning here is just make sure you state restrictions. It's the first thing you do before you do any simplification, all right? Because this is the problem that was proposed to you. This was not given to you. That was not, we were not asked what log x squared is to begin with, all right? Okay. So I write it down the first step for you. Log x squared equaling log 8 plus log 2. Well, what do we see on the right-hand side here? Let's put that as a single term, okay? So on the left, we still have log x squared. On the right-hand side, if we put that as a single term, that's going to be log, same base, right? Because all these are the same base, 10 and 10, right? So on the inside, you're going to have 8 multiplying 2. And then that simplifies to 16. So log 16. Okay. So there's two ways to think about this now. Imagine I gave you the problem x squared equals 16. Right? Well, you can apply the logarithm and operation to both sides just as easily as you can take an operation away from both sides, right? So because the problem is log x squared log 16, well, I see that I'm asking to take the log of both sides. Well, I can just remove those logarithms, right? And I can write it as x squared equaling 16. But you could have also seen it as, well, let's rewrite the problem. Log x squared log 16. You could have also approached it the same way we've been doing in the previous problems, where when you want to get this last step, x on its own, you write it as an exponent. So I write it as 10 to the power of x log 16. So x squared is 10 to the power of log 16. And then when we learned all our basic properties, this was property number 4, which says when you have the same base here and here, right? So that technically is a 10 up there. It is just equal to whatever is on the inside here. So x squared equaling 16. So 2 ways to go to the next step, okay? Like getting down to x squared equaling 16, you could have approached it either way. So now that we're at this step, x squared equaling 16, let's apply a square root to both sides. And recall, whenever you take a square root, you are going to get 2 solutions. You are going to get a positive version and a negative version of the value of the root. So that means you have one scenario where you need to check, does positive 4 work? And you have another scenario where you have to check, does negative 4 work? So then go back up to your restriction. And in this case, we said it was x has to be bigger than 0. So that means this right here is not valid. And we only have a single solution to our problem. All right, example D. Log 6x plus 1 plus log 6x plus 2 equaling 1. In this problem, which is different from the previous ones, we now have 2 terms that have unknowns in it. So we need to write 2 separate restrictions. So if we are stating our restrictions, I have to look at the first term, which on the inside is x plus 1. So when is that bigger than 0? Well, that says x's need to be bigger than negative 1 to work. And you have the second one, which says x plus 2 bigger than 0. And this constraint is saying x's have to be bigger than negative 2. Well, are both a restriction? If I choose a number, let's say I chose a number, like after I went through and I solved this, and I get a number, being like negative 1.5. Well, if I went up here and I said, okay, is that solution valid? Well, negative 1.5 is a number that is bigger than negative 2. But it is not bigger than this. So I'm satisfying this constraint, but I'm not satisfying this constraint. And if we think about a number, any number that's between these two constraints, let's put them on a number line to see, okay? So if I have negative 2 here, and I have negative 1 here, I have 1 saying, hey, numbers need to be bigger than negative 1. This is your x plus 1 restriction. And then I have the second one that's saying, hey, numbers need to be bigger than negative 2. So what you would do is you'd say, okay, well, let me look at this constraint right here. Let me look at that one. That means I'm going to test numbers like negative 1.7, negative 1.5, dot, dot, dot. Any number that exists essentially between these two numbers here, right? Well, none of those numbers are going to satisfy this constraint right here, because you're ultimately telling me that x's need to be bigger than negative 1. So it doesn't matter what numbers like you substitute in here, because nothing that exists between negative 2 and negative 1 will satisfy this constraint here. So if you think about it in terms of like dominance, like which one is more like dominant, like which one is telling you this is the true restriction, it's going to be this one, because anything that satisfies this constraint will also satisfy this restriction here, or constraint, okay? And let's look at that for example. Let's say we went through the problem and we got a number that was like negative 0.5. Well, just as we did in previous lessons, we go and say, okay, well, does that satisfy our two restrictions? Well, yeah, it satisfies that one. And yes, it also satisfies that one. And that would be true for all numbers, okay? So because both of these restrictions are pointing in the same direction, they are both going larger than their negatives, you go to the one that is more dominant. This one, the one that is more to the right, okay? So this one right here, that would be the governing restriction, the one that would satisfy both constraints. So when you have overlapping restrictions, all right, you can think of it in a number line, but then go to the one that would be more to the right, okay? Like the one that would always be the case. So that is this one right here. So now we've stated our restriction. And again, if this confuses you, just start and then we'll talk about it in class, okay? But as we move forward, let's go through and solve this problem. Well, just in the previous problems, we need to get x on its own, right? I'm not going to take this term and bring it over to one side, because I would bring x on one side and 1 on the other, so that doesn't work. But again, pattern recognition, you'll see that, okay, well, I have a log being added to another log, and both of these have the same base. So I'm going to apply my product law. I'm going to rewrite it as log base 6, and I'm going to take my first bracket, so like this would be like m, and I'm going to multiply my second bracket. Think of that as like n. So I'm going to multiply x plus 2. And I'm going to write that as equal to 1. All right. Well, now let's get rid of our logarithm. So I'm going to take that 6 and put it to the power of 1. So that's 6 to the 1 equaling x plus 1, x plus 2. Well, when do we see this? When do we see, two x's with separated by brackets multiplying each other? Well, this is leading towards quadratics, right? And in quadratics, we had to have our two brackets, like x plus 1 and x plus 2. But remember, there needed to be a 0 here. When you're solving a quadratic, you need to have a 0 on one side. So I can bring the 6 over, right? So 6 to the 1. I could bring that over, and I'll rewrite this problem as 0 is x plus 1, x plus 2, minus 6. You have a 0 here, so you're like, okay, cool, I'm going to state my factors. But no, this is not factored form because you have this term on the backside here. So we first need to expand out and then we put it back into factored form. Because you have to see, well, when we expand out, what is our new c term? Like what is ax squared plus bx plus c? What is that term right there? Once we figure out what the new one is, because we have this minus 6, we will then put it back into factored form. So if I expand that out, that's going to be 3x plus 2, and then minus 6. So then you get x squared plus 3x minus 4. Okay, so there's your new c term. So now let's factor the problem. So if we factor this, all right, you're going to get, what, two numbers that add to 3 and multiply to negative 4. So that would be x plus 4, x minus 1. Okay, so again, if you went here, you just brought that 6 over and you stated your factors here to solve the problem, you would have got minus 1 and minus 2, but that's not true. The true solutions to our problem are x being either minus 4 or x being 1. So these are the solutions to the problem. Your two solutions. But as we've done in previous problem, you have to validate them. Go back and you say, okay, well, negative 4. Does that satisfy this, the dominant constraint? No, it doesn't. So this one is actually not valid. But positive 1 is a number bigger than negative 1, so that is your only solution. So we have one solution, right? So two possible algebraic solutions, but in reality, this one is an extraneous root. Right? Like another way you'll see it sometimes if you look up online, is people will call this an extraneous root. Essentially just saying that that's not valid. That is a solution, a root, that does not work for the problem. Okay, E. We got 2 more to go. Log 4 of log 2 of log 3x equaling negative 0.5. So we need to know what is our restriction on this x right here. But if we think about what's going to happen algebraically, you're going to work BEDMAS. So you'd have to go in the inside bracket. So whatever value you solve for x, this is going to spit out some number y. And then the next operation would be saying, hey, take log 2 of y, whatever the output of that first one is. Okay? And then whatever this spits out, this will spit out like, I don't know, some number like z. The last thing would be saying, hey, you're going to take log 4 of z. And this z right here, right, cannot be a negative number. So if we think about where that z came from, you almost have to go back up the chain. Okay, well, the z came from this operation here, and that operation there came from the inside here. So when we are figuring out what is our restriction, we need to go back and look at the entirety of this bracket here. So the entirety of it, because that is all contributing to this final operation that occurs. So I am looking at when does, the inside of the square bracket there, that's what I've written here, when is the inside of that square bracket going to be bigger than 0? Okay, so let's get rid of all this now just because it's going to make our math later messy. So we are looking for when the inside of the square bracket is bigger than 0. So just undo all the logarithms, all right? You would solve this as a picture like being like an inequality here, right? So then if I want to undo, I'm going to write it first as 2 to the power of 0. So that's log 3x. Well, 2 to the 0 is going to be a value of 1, right? Anything to the power of 0 just has 1. Then I undo this operation, 3 to the 1. Well, then I get x having to be greater than 3. So that is your restriction. If we make sense of that solution, or sorry, that restriction, x being greater than 3, and we go back to our logarithms, if you see that if we take some number that is bigger than 3 and plug it in for this x, so for example, if I took log 3 of 4, 4 is a number that is bigger than 3. And let's say that was one of our solutions we found, okay? Well, whatever this computes to on your calculator, remember that is going to be the input for the next logarithm, right? It's going to be the input for that log 2 of whatever it is. So this right here, if you put that on your calculator, right? Well, I'll show you how to use them, not log base 10, but if you were to calculate that, you would get a number that is bigger than 1. It would be something like 1 point, I don't know, something like that. I actually don't know off the top of my head, but it would be something like that. Okay, 1.001. Well, then you'd be saying, okay, well, what is the what is this equal to? And remember, that is the input for the next logarithm, the log 4 one, right? So whatever that ends up computing to would be your input for log 4. And so that number would be a number that's ever so slightly bigger than 0. So you'd have a number that would be like 0.001 or something. And then this is a valid solution. Like you can calculate this. Log base 4 of 0.01, you're going to get a really large negative number. Right? It's going to be like, I don't know, like negative like 10,000 or something. I don't know, whatever. But the point is that you get a number, right? And so when you're validating solutions of x, and as long as the number is bigger than 3, this operation of logarithm can occur. This logarithm operation can occur. And this one can occur. Okay, so you're not gonna, math is not gonna break down. So that's what we just did, okay? Now let's go back to the problem. We're solving for x, right? Like these whole things are set up so like let's find that solution of x. So at this point now, we are just gonna isolate for x. We're gonna take the 4 and put it to the power of 0.5. So 4 to the 0.5 is really just the same thing as me saying 4 to the half. And that's going to be equal to what's left over, so log 2, and that's going to be me doing log 3 of x. Well, 4 to the half, that's the same thing as 2, right? You're essentially taking the square root of 4. And I'm going to write that as log 2, log 3x. And now, if I undo this logarithm right here, so I write it as exponential, that's the same as me saying 2 to the power of 2. And then what's left over is log 3x. Well, 2 to the power of 2, that is 4. So I have 4 being equal to log 3x. And then lastly, I can get rid of this logarithm here, so I get rid of that like 3 in essence. So that's 3 to the 4 being x. So that means my solution is x being 81. And then you check, does that satisfy your constraint? Yes, it does. So meaning that if you were to take 81 and you plug it in here, all of these logarithms will work. All right, we showed you that. And then you remember what these solutions mean, that like after you do all those logarithms, you'll end up getting an answer of 0.5. Okay, last one. And I want you to start this question, okay? Because I am 100% going to test you on this concept, all right? So what makes this one special in terms of all the other problems is we have to check a restriction on a quadratic, okay? So what's on the inside of that logarithm there is x squared plus 48x. Technically, there is still a 1/3 here because it is the third root. And we have to check when is that bigger than 0. So if I am isolating or trying to figure out what values of x satisfy my inequality here, well, let's get rid of that 1/3 exponent. So essentially that means I'm going to just cube both sides. And I get x squared plus 48x being bigger than 0. Well, this is a quadratic, okay? This is a quadratic that has a positive a value. So it is going to be opening up. But let's get just a rough picture of what it looks like, right? Well, let me put it in factored form. So I'm going to factor out an x, and I'm going to get x plus 48. And that's going to be bigger than 0. So I just said you have a quadratic that's opening up, but this tells me that I have a 0 that occurs when x is 0. And this root, or that factor, tells me I have another 0 when it is minus 48. So because this is an opening up parabola, it's going to go like this. And you can see, let me extend my graph, that when you are to the left side of 48, so when we are in this region right here, we are in the positive y space. So any x coordinate, like let's say minus 49, minus 51, so on, well, these will always result in positive outputs, all right? So they will allow you to compute this logarithm here. That's what you're finding, all right? And the same thing, you can also see that on the right side of 0, so when x is bigger than 0, you are also going to be in the positive y space. So we have two valid restrictions, all right, or two restrictions. We have one restriction that says, hey, if you get values of x that are less than 48, you're going to be allowed to compute that logarithm. And then the other restriction says when you get x values that are bigger than 0, you're able to compute that logarithm. But anything that is in between those two numbers, we can see, like all this space right here, right? Any number that exists between them, well, that's going to cause this logarithm right here to break down because it will ultimately give you a negative y, or negative output, and you cannot take the logarithm of a negative output. So the whole purpose of setting up your restrictions, okay, so don't get lost in this inequality that we just did here. Like, if you think big picture, what you just did is you said, all right, I'm going to go through my math here, and I'm going to get solutions for my x, right? Well, if I was to put those values of x back into the problem here and here, would I have the log of a positive number, or would I have the log of a negative number? Well, our restriction says, as long as the x's you are finding satisfy these restrictions here, so there's a number that is either less than 48 or bigger than 0, you're going to end up taking the log of a positive number, which will allow you to calculate that answer, okay? So we've stated our restrictions. We figured that out. In this case, we have two restrictions that could work, but now we just need to solve the problem. We need to find those values of x. So remember, this is a base of 10. So I'm going to write it as log base 10, just so you can see it. And I'm going to write this as x squared plus 48x, and I'm going to put that as 1/3. Okay, I'm going to rewrite that root as a fractional exponent, and that's equal to 2/3. I'm going to use my power law and bring this 1/3 down in front. So this is going to be written as 1/3 log base 10 x squared plus 48x equaling 2/3. And why did I bring use that power law to bring that down? Well, I was able to see that if I brought it down, I can essentially get rid of these denominator 3's. Because I have a denominator 3 on both sides, or mathematically it's like me saying, hey, take both sides and multiply by 3. I can cancel them out, okay? So then I'm left with 1 times log 10, but it's just log 10, x squared plus 48x, and that's equal to 2. Oh, I have 2 equal signs. That is not the correct way to do math communication. Sorry. So that is, I have log 10 x squared plus 48x equaling 2. I'm going to rewrite that as 10 squared equaling x squared plus 48x. That's 100 equaling x squared plus 48x. Bring the 100 over to the other side. So I have now 0 x squared plus 48x minus 100. This is a quadratic. So we are solving that quadratic. We need to factor it. That is x plus 50, x minus 2. So our solution to our problem is saying, hey, when you take a value of x minus 50 and you plug it in for this x here and this x here and do the logarithm, you'll get 2/3. That's what you just found. And you also found that if you do the exact same thing, but you do it with x being 2, you will also get 2/3. And then check, do both of these satisfy your constraint? Well, a solution of x being 2, that is on the right side. So yes, that is a valid solution. And x being 50, minus 50, sorry, that is also going to be in the positive y space. So both of these are valid solutions. Okay, and that is it for today's lesson.